Alright guys, I decided to make a short video for you showing you a few applications, things that you can use Stellarium for students of various ages in a classroom or as homework. I'm locking my toolbars onto the side here because that's the way I prefer them to be, just by clicking on triangle buttons and turning them into squares. I haven't done anything yet, but I'm assuming that you already know how to change your location. My location is mine already, and I'm assuming you know how to change the date and time. I'm going to change this date and time. Actually, I'm going to pause first so it doesn't move on me. Change my date and time to midnight on August 11th. The reason why I chose August 11th is because there's a meteor shower around this time, 10th through the 13th, some point in there, called the Perseid meteor shower, and it's very reliable and pretty amazing compared to a lot of the other meteor showers. I think they said 60 to 100 shooting stars an hour. Don't quote me on that, but it's pretty amazing to see, so I wanted to show you what the sky would look like that night and how we can use Stellarium to figure out what else we might want to look at. So saying you're bringing out a bunch of students that night to look at the sky, what might you want to see? Well, first of all, you want to see the meteor shower. Perseus, because they are the Perseids, they will be in this direction. So if you look towards the constellation Perseus, that's where these meteors are going to be centered. It doesn't actually have anything to do with the constellation Perseus, except for this is the general side of the Earth that is running into this comet debris, and it's from the comet Swift-Tuttle. So that is where you would look for the meteors, but you might also want to look around at a couple other things. You could, if you wanted, observe the Andromeda Galaxy, which is actually not very far away from Perseus, right here. And you could use the Great Square of Pegasus to help you locate Andromeda and Andromeda Galaxy, which is going to look kind of fuzzy, just a fuzzy object, unless you can look at it with binoculars or a small telescope, and you might be able to see a little bit more detail. And this is actually pretty much the farthest object that you can see with the naked eye. It's 2.4 million light years away, which is kind of neat if you just think about it that way. So you might also want to observe, which will have to be a couple hours later, the Pleiades. This little star cluster, if you look at it, it looks kind of like a tiny little dipper. And it's unique because these are all reasonably bright and all really close together, so it's easy to identify the Pleiades. This is an open star cluster in our galaxy, and one kind of neat thing you might like to know is that the Japanese word for the Pleiades is Subaru, and if you notice that the stars kind of look like the logo for Subaru. So, if you're out observing this night, you might want to see a planet, if there are any planets out. I'm going to use the ecliptic to help me locate the planets, because the planets will always be along the ecliptic. So apparently Uranus is out that night. Looks like that's the only one that you'll be seeing. So maybe you can use a small telescope to find the planet Uranus. That could be fun. So that's one thing you can use Stellarium for. You can use Stellarium to find out what you would actually see in the sky at any particular night you choose. Okay, possible application number 2. You could use Stellarium to train or to let your students investigate what motions the moon will do, or what motions the sun will do. We're going to look at the moon. Let us choose a different date. No, actually we can keep it the same for now. Let us find the moon first. Search window. I'm just making it easier on myself. Okay, moon's underneath. Let's look at the horizon a little flatter. How about that? That'll be this button. Markings, landscape, ocean. So I'm just changing my ground. It doesn't actually set me in the location of the ocean. I am still in Kalamazoo. But now I can see the horizon as a flat line instead of all the trees and buildings in the way. So the sun has just gone below the horizon. And I see the moon here. I want to observe it also right on the horizon. So if you had your students say, what is the moon going to look like if you're looking at it as the sun is setting? If you want to use a more specific time, then I would suggest using 6 p.m. So we can watch how the position of the moon changes, how the phase of the moon changes over the next month when the sun is just setting. So, if the moon is on the horizon and the sun is just setting, you know the moon is going to be in an almost new phase. I don't know if you can see that, but that says 4.5% illuminated. So it's almost new. A couple days later, however, the moon is moved up. You see that up in the sky, and it is at 16.4% illuminated. It's also moved more, and this is direction south. And you can see how the phase is different, and also notice that the brightened side is towards the sun. Okay, so I'm going to lock on the moon here. That's this button. It makes whatever object I'm clicked on the center, and when I change the time, oops, it just stays centered. Okay, so now we see that it is 34% illuminated. A couple more days, more than half illuminated. We've seen that it's sort of curved up, that the phase is extending out. This way it's still lit towards the sun. It's going up and it's going to start heading back down, but it's moving southward. So it's still moving up, and now it's 78% illuminated. We can even look at it and see what side is dark. A couple more days later, almost a full moon now. And you notice it's starting to head downward. Now it's considering this a full moon. So this is just a little bit above the eastern horizon, and we have the sun setting just below the western horizon. So right now, when the moon is full, it is on the opposite side of the Earth as the sun. So this is important to know because you can't ever have a full moon at noon. You can't really have a full moon while the sun is also in the sky. They're going to be on opposite sides of the horizon, always. Likewise, you can't see a new moon at midnight because it's going to be on the same side of the Earth as the sun. They hang out together. So if we want to watch a whole lot more of this phase, and you see now the moon is below horizon, we can't see it any more of that at this time, at this sunset time. So if we want to watch the rest of this cycle of the moon, why don't we change our time to sunrise? There we go. Sun is starting to rise. So I've just moved this forward. This is the very next day. And let's find the moon. It's going to be right there. 92% illuminated. So what you can have your students do is draw two pictures of what the moon does just as the sun is rising and just as the sun is setting. And we can watch the moon go through its phases. So we're actually going to watch it go to its new phase. Lock onto it, and you already sort of know the motion. It's going to curve up and over. It's going to go from west to east. But here you can see how the phases change, and you'll notice getting to the new moon phase, we're getting close to the sun. So this could point out a couple important things that your students might not know. How the moon moves, how you can't have a new moon at midnight. Well, you can't see the new moon at midnight. You can't see a full moon at noon. And what side of the moon is lit up according to what we can see. It's going to be this side towards the sun. Yeah, so those are a couple of points that are kind of hard to know just from personal experiences. They could go out and observe this, but using Stellarium you can do this in 10 minutes instead of a month. Something else you might want to do using Stellarium is watch the sun. What does the sun do? This is a little bit more difficult to see. We're actually going to take off the atmosphere, so it doesn't blur everything. Where the sun is located in the sky at sunrise on the equinoxes and solstices. Why don't we look at that? So let's start with the summer solstice. Sunrise. See the location? It's over here to the east. Actually, there. Summer solstice. Now, fall equinox, which is a little bit later, which makes sense. Sunrise is a little bit later. And you see it's rising very close to directly east. Now, it's not directly east, but it's very close. Then, where it's located in your winter solstice, rising even a little bit later, and it's located south of east. And like you probably expect, spring equinox, it's going to rise very close to due east. And this applies to when it's setting. It's going to be setting very close to due west on the equinoxes, and it's going to be setting south of west on the winter solstice and north of west on the summer solstice. So you can sort of examine that. You could also possibly show your students how the sun is higher up in the sky in the summer versus in the winter. One good way we could show that is to turn on our meridian, this line that goes directly from south through the zenith to north. And let's get the sun so it's on the meridian. That's going to be the highest point in the sky it is at that time. So, and that's going to be probably pretty close to noon. Not always exactly, but pretty close. Okay, so here we have spring equinox. A couple months later, 3 months later, summer solstice, fall equinox, and winter solstice, and we kind of have it shifted over, and you want to know why that is? That's called daylight savings time. It's already built in. So you can show your students how the sun is a different height at these different times during the year. That's a useful thing you could have them do. So we looked at motions of the sun and motions of the moon. Why don't we look at motions of the stars depending on your location on the Earth? Because it's not that easy to travel all over the Earth unless you're using Stellarium. Then it's really easy. So I like to turn on my equatorial grid when I do this. So this is centered on the North Celestial Pole, which is this point right here. And you'll notice how Polaris is really, really close to the North Celestial Pole. That's why it's called the North Star. It's almost directly north. If we move our time forward, now we can see how the constellations are moving. You'll notice how they're traveling counterclockwise around the North Celestial Pole. So now you can sort of predict where the constellations are going to be located. They're going to make one full turn in 24 hours because it's due to the rotation of the Earth. So if you're looking due west, all your stars are going to be traveling right. Down and right is what they're doing. Or up and right from the east. Left to right around the South Celestial Pole, which is going to be underneath your horizon. You can't see that from our location or from a location in the Northern Hemisphere. But what would we see if we were instead observing from the North Pole? Here we are on the North Pole. Every direction we're looking is now south. And no matter what direction we look, our stars are going to be moving parallel to the horizon from left to right. They're going to be traveling counterclockwise around the North Celestial Pole, which is directly above us at our zenith. And you might then realize from that if we went to the South Pole, they would similarly be traveling from right to left, the opposite direction, because now we're on the bottom of the Earth. Comparatively, traveling around this South Celestial Pole, which there isn't a star to correlate, so there's no South Star. But all the stars will be traveling parallel to the horizon and from right to left. So what if we were somewhere in the South Hemisphere? Now, the stars are still traveling in the west. They're traveling down, but they're going down into the left, the opposite of the direction that they were when we were in the Northern Hemisphere, which was this way. So that's important to know. You could tell pretty much wherever you are on the Earth by paying attention to how the stars are moving. So now you will have the South Celestial Pole in your sky, and the stars are moving clockwise around your South Celestial Pole. They're moving counterclockwise around your North Celestial Pole, but it is underneath your horizon. And I'm pretty sure you guys can then determine our last location on the equator. The stars are traveling counterclockwise around our North Celestial Pole, which happens to be directly on the horizon, as is the South Celestial Pole. Stars will be traveling straight down in the west and straight up in the east. So, how stars move, depending on your location. Something you could have your students go over. Okay, let's do a couple more things, but we're going to change our location to Io. Io is a moon of Jupiter. As you can see, we're looking at Jupiter. And I want to show you something really interesting about most moons and their orbits. So, you see here we have Jupiter, which is pretty much directly above us, pretty straight up, and we're going to watch it over a few hours. So, there's the sun, and the sun is setting. We're noticing that Jupiter is rotating. Sometimes we see the red spot, sometimes we don't. We see Jupiter going through phases. But what you notice is Jupiter is always in the same location. You see that? It's still above. It's not setting, it's not rising, it's just up above us right now because of where we are on Io. Well, what happens if we move? If we move, Jupiter changes. But Jupiter doesn't change if we're staying in the same spot. Now, do you know why this happens? This is because the moon is tidally locked to Jupiter. Most moons are tidally locked to their planets. This means that the same face, the same side, always faces the planet. So if you notice, we have something called the dark side of the moon. That's because there's a side of the moon we don't see. It's not because it's actually dark. It's because we don't see that side. The moon is tidally locked to the Earth. And so, as Io orbits around Jupiter, it turns in its rotation the exact right amount to always keep facing Jupiter. Jupiter can spin at its own rate, but Io, as it orbits, turns just enough so that it's always looking at Jupiter from the same side. So if we traveled instead to the other side of Io, we would never see Jupiter because it would be always facing away. We would see the sun, but we would never see Jupiter. So you could teach your students about tidally locked moons. Planets can also be tidally locked to their suns if they're very close. Next, why don't we talk about retrograde motion? And why don't we go to Mars to talk about retrograde motion? Mars is a planet that we usually talk about seeing perform retrograde motion. And we can observe retrograde motion happening in planets that are either closer to the sun than we are or farther. Mars is farther from the sun than we are, but if we're on Mars and we look at Earth, Earth is closer. Retrograde motion happens in either case. That's important. Now, what is retrograde motion? I want to change my landscape because we're on Mars now. Let us find the sun. Okay, it's below the horizon. Now it's not. Okay. Retrograde motion is when a planet appears to move backwards compared to the stars. Now I'll show you, if we look at it just via per hour, everything's moving together kind of just as one. But if we go by day, we can tell that the sun, the planets, and the stars are all traveling at different speeds. You notice that? So if we watch the planets, they're all moving forward, same direction as the stars. But Mercury's moving back. Now Venus is moving backwards, and Earth is going to move backwards in a moment. So you can actually see this retrograde motion happening. And you can kind of picture how these planets are moving in orbits. They're orbits around the sun, and that there's a part where they're moving past Mars in their orbit. Mars is kind of trucking along on its outer, longer, slower orbit and watching as the closer planets kind of orbit around faster. That is retrograde motion seen from an outer planet. The same thing kind of happens if we're watching from Earth as this happens. Mars will appear to move, and then as we start passing by it, it looks like it moves slower and backwards. And then when we finish passing by and we kind of start heading around on the other side of the sun, Mars moves back. Looks like it's moving in the same direction it was before. So this is retrograde motion. This is kind of just seeing it from the outside. So you could also do that with your students. And that's pretty much all the suggestions I have for you guys today. There are several different locations you can go to. Lots of different moons, even comets, asteroids. We have Vesta, which is an asteroid. Quaoar. This dwarf planet, which is one of the ones outside of Pluto's orbit, kind of helped with the whole demoting Pluto, and as well as Sedna. You could look at this C2006P1. This is a comet that has escaped the solar system. So you can watch it as it gets close, and then it goes far away and never comes back. I would like right now to look at Mimas. And why? Because Mimas is close to Saturn. Look at that. So this is kind of fun. We could watch as it orbits around Saturn, and you'll notice that its orbit isn't completely aligned with the rings, because sometimes it's above them and sometimes it's below them. But yeah, you can look at all these different locations that you can actually go to in real life, and you can go to Pluto. And where is Pluto's moon? Look at its moon. And this is kind of neat. You could use the parent diameter right here. You could use 3 degrees, 36 arc minutes, 12 arc seconds. You could use that, and you could use trigonometry to determine how big it is. Or, you know, if you have the distance, you can figure out how big it is, or if you have its actual diameter, you can figure out how far away it is. So that's another thing you could do with your students. So that's all I'm going to go over. This is not quite half an hour, so that's excellent. And I hope this wasn't too confusing and was a little bit helpful, showing you guys a few of the things that Stellarium can be used to do. Thanks for watching. It's actually not very far away from Perseus, right here. And you could use the Great Square of Pegasus to help you locate Andromeda and Andromeda Galaxy, which is going to look kind of fuzzy, just a fuzzy object, unless you can look at it with binoculars or a small telescope, and you might be able to see a little bit more detail. And this is actually pretty much the farthest object that you can see with the naked eye. It's 2.4 million light years away, which is kind of neat if you just think about it that way. So you might also want to observe on August 11th. The reason why I chose August 11th is because there's a meteor shower around this time, 10th through the 13th, some point in there, called the Perseid meteor shower, and it's very reliable and pretty amazing compared to a lot of the other meteor showers. I think they said 60 to 100 shooting stars an hour. Don't quote me on that, but it's pretty amazing to see, so I wanted to show you what the sky would look like that night, and how we can use Stellarium to figure out what else we might want to look at. So saying you were bringing out a bunch of students that night to look at the sky, what might you want to see? Well, first of all, you want to see the meteor shower. Perseus, because they are the Perseids, they will be in this direction. So if you look towards the constellation Perseus, that's where these meteors are going to be centered. It doesn't actually have anything to do with the constellation Perseus, except for this is the general side of the Earth that is running into this comet debris, and it's from the comet Swift-Tuttle. So that is where you would look for the meteors, but you might also want to look around at a couple other things. You could, if you wanted, observe the Andromeda Galaxy, which is... Alright guys, I decided to make a short video for you showing you a few applications, things that you can use Stellarium for students of various ages in a classroom or as homework. I'm locking my toolbars onto the side here because that's the way I prefer them to be, just by clicking on triangle buttons and turning them into squares. I haven't done anything yet, but I'm assuming that you already know how to change your location. My location is mine already, and I'm assuming you know how to change the date and time. I'm going to change this date and time. Actually, I'm going to pause first so it doesn't move on me. Change my date and time to midnight, which will have to be a couple hours later. The Pleiades, this little star cluster. If you look at it, it looks kind of like a tiny little dipper. And it's unique because these are all reasonably bright and all really close together, so it's easy to identify the Pleiades. This is an open star cluster in our galaxy, and one kind of neat thing you might like to know is that the Japanese word for the Pleiades is Subaru, and if you notice that the stars kind of look like the logo for Subaru.